Hello, everyone. Today we will continue our discussion in the topics of magnetic circuits. So just a quick revision for what we have discussed in the previous session. So in the last session, we discussed the basics of magnetics, and we discussed what the meaning of permanent magnet and electromagnet. And also we discussed the different relations used in and parameters used in magnetics topics. We discussed the meaning of flux, the flux density, flux intensity, the flux linkage, and inductance. And later on, we will elaborate more in inductance. And we discussed the meaning of MMF and how can we calculate the relations and parameters in these relations. So MMF or magnetomotive force equals Ni, where N is the number of turns of the coil, I is the electrical current, and also equals H, flux intensity, times L, which is the average length of the magnetic path. And this is also equals phi, which is the magnetic flux, times reluctance, which is the equivalent resistance of the magnetic core. And we discussed some examples of magnetic circuits like the toroid, and we also gave a quick discussion about the magnetic materials used in electrical machines, and this is most probably the shape of the magnetic rotating machine that we will see in our class in the different motors, in DC motors, in induction and synchronous motor. And also we convert this magnetic circuit into an equivalent circuit, and we draw the relations together. Let's start solving a first numerical example here. So in this example, guys, in this figure, we have two magnetic parts. The left magnetic part is C shape, and the right magnetic part is I shape. So this is CI shaped magnetic circuit. Also, as you can see, the left side is connected to an inductance or supply of electricity and this number of turns. Once we supply this with a certain electric current, so a flux will start moving, and you know that flux prefer to move in magnetic material because it has lower reluctance compared to the air. So flux will start moving here inside. What this spring means here for us, this means the I-shape part is free to move in the horizontal direction. So in this direction, left or right, let me the pointer. Yeah. So in the X direction, like that. Okay. And the C shape, since it's connected already to electricity here, so we consider this part as a stationary part. So the I shape is moving part, the C shape is stationary part. You can see here also, guys, like two wires with two terminals here, and this I shape has like latch or like arm. This arm, if the I shape moves to this direction towards the C shape, so this will make short circuit on the two terminals right here. So this is, guys, we call this structure as a relay. So this is called magnetic relay or electromagnetic relay. The relay is used in control and sometimes in protection. And the same concept of the relay exists also in circuit breakers. So circuit breakers are used to connect or disconnect electrical circuits. And at the same time, it's used for protecting electrical circuits, like the circuit breakers you have in your electrical panel in homes. So this is also work with the same concept. So let's see this example here and investigate the performance of this circuit here. So the example says the figure below represents the magnetic circuit for a primitive relay. This relay, as you can see, the coil has 500 turns. So this coil has 500 turns. And the mean core path is L core equals 360 millimeter. So the average length of the magnetic path through all the magnetic or core parts equals 360 millimeters, including the C shape and I shape. When the air gap lengths are 1.5 millimeter each, so if we have two air gaps, as you can see here, each one is 1.5 millimeter, what happens? A flux density of 0.8 Tesla is required to actuate the relay. Actuate the relay means attract the I shape to the C shape and makes this air gap equal 0. So this is the meaning of actuating the relay. Actuating the relay means the C shape attract the I shape in order to make short circuit on these terminals. So making the short circuit on these terminals will allow another circuit to connect electricity. So this is the concept of the relay. Okay. So again, the parameters we have right here, at a distance of 1.5 air gap, we have 0.8 Tesla. Or we need 0.8 Tesla. Why we need this amount of flux? In order to attract the I shape to the C shape direction and make short circuit. So this is the amount of flux needed at this distance of 1.5 millimeter. Let's see what are the requirements here. So first, find the current in the coil. So we have a certain magnetic flux density, guys, which is 0.8 Tesla, and we need to know how much current we need in order to establish this 0.8 Tesla in our core. So this is simply the first part of the question. So let's, guys, use our relations to solve this question. Let's firstly write our relations together right here. So, guys, our relation is MMF equals N times I equals H times L equals phi times reluctance. So this is our relation that we are using in these problems. And if we go back, or let's copy this circuit in front of us here. So if we would like to make a magnetic equivalent circuit for our magnetic core, so we would say that we have a source of MMF here. So this is F, or the magnetomotive force. And then we have core and air gap. So we can say that we have one reluctance for the core and another reluctance for the air gap. And then the path will return back again, or the flux will return back again to the source. And the amount of flux is moving here is phi. The given data again, B equals 0.8 Tesla, N equals 500 turns, and L core equals 360 millimeter, and length of the air gap. So he mentioned that 1.5 distance, which means 3 millimeter air gap distance in this case. So let's see if anything else is given here. No more data are given here. Yeah, actually there is a given data here, which is, we forgot to read this part. The core is cast steel. So the core is cast steel. So we can use the BH curve from the cast steel. So this would be given in the question in exam. So we know now these data, and we have also the curve of the BH. So BH data are given, and we can use our curves now for the cast steel to see the required value of B and H. So if we see this relation here, guys, the requirement first thing is find I. In order to get I, we know the value of number of terms. So which term we can use now? We have H, sorry, we don't have H, we have L. We don't have phi, we don't have reluctance. So the given data, as you can see, we have the magnetic flux density. Even we don't have the cross-section area. You know that B equals phi divide A. We don't have the cross-section area in order to get flux and use this term. And you don't have also the reluctance. And since you don't have the cross-section area, you cannot get the reluctance as well. So it seems like this term is not easy to be used for the time being. However, we have B, and we have the magnetic curve or the BH curve of the cast steel. So what we can do is, let's get the value of H poor at 0.8 Tesla from the cast steel pH curve. So this is the task now. How can we do that? Let's go back to the cast steel characteristic here. So this is the cast steel, this curve at B equals 0.8. So this is the 0.8 value. So it would be 500 something here, maybe 510. So in this case, we can say the value of H, so H or equals around 500 turn, and H is measured in ampere turn per meter. So this is the value of H poor. Is it gonna be the same of H in the air gap or not? So we discussed before, guys, phi in the air gap is the same phi in poor. And we assume all of the time that cross-section area is constant for the air gap and for the core, which means we can say that B core equals B air gap. However, you know that B equals mu times H, and mu is mu naught times mu R times H. So this is the relation. So how can we elaborate now? So if you have a look here, now we mentioned that B core equals 0.8 Tesla, and we could get the value of H core from the curve, which is 510. Now, we can say the MMF part of the core equals H core times L core, which is 510 times 360 millimeters. So this is going to be 0.36 meters. So this is the amount of magnetomotive force that we have through core only, but we still need to calculate the magnetomotive force through the air gap. How can we get it? So simply we can say F air gap equals H in the air gap times 2 lg. Lg is 1.5 millimeters, so we can say the overall air gap length is 3 millimeters. So we can say B gap divide mu naught. So since B gap equals B core, because we assume that B is constant, so because we assume the area is constant, so we can say H gap equals B gap divide mu naught. So 0.8 divide mu naught only, which is 4 pi times 10 to the power minus 7. And we can obtain the amount of MMF of the air gap part. And this is the number here, 1910 ampere turn. Now, guys, before we continue and getting the current, we need to sense the meaning here. So can you see, guys, the amount of force needed in the core of 360 millimeter is 184 ampere turn. However, for only 3 millimeter, the amount of force needed to create the same amount of flux is more than 10 times the amount of the core in only 3 millimeters. So this means you need huge energy in order to establish the same flux in only 3 millimeters air gap. Why? Because again, the air gap flux resistance, which is reluctance, is going to be much higher compared to the magnetic material. We mentioned before, guys, mu r for magnetic materials we use in most of our applications could be from 2000 to 6000. So this means the magnetic flux resistance or the reluctance of the air gap could be 2000 to 6000 times of the magnetic material. So the reluctance of the air gap is expected to be 2000 times to 6000 times of the magnetic flux reluctance of the core. So this is the reason why we have huge, or we need huge force to establish the same amount of flux in the air gap. Now, in order to continue and calculate the current, so you know that from Ampere's law, we mentioned that summation HL equals NI. So summating HL, or the force in our magnetic circuit, so F core plus Fg equals total F, which is N times I. So this is the total MMF, 2094 ampere turn. So now we can use the number of turns, 500 turns, in order to calculate the required current. So this means in order to establish a flux density of 0.8 Tesla in our relay, we need 4.19 ampere. But take care, this is only at a distance of 1.5 millimeter apart from the C shape. So the I shape is 1.5 millimeter distance from the I shape. Okay, nice. So this is the first part A. In B, the example says compute the values of permeability and relative permeability of the core. So we need to know the values of permeability, which is the total permeability, and the relative permeability as well. You know that mu equals mu naught times mu r. And mu naught is constant, 4 pi times 10 to power minus 7. So after getting the permeability, we can calculate the relative permeability. So how can we get the permeability? So simply, guys, permeability of our core equals P divide H. We have already B is given, and we got H from the curve. So we can just divide B divide H. So the value of the permeability of our core is 1.57 times 10 to power minus 3. Now, we can calculate the relative permeability. As we mentioned, the absolute permeability is well known. So just divide over the absolute permeability, you can get the value of the relative permeability. So the relative permeability is 1250 for this core. Take care that this value is not constant for the core all of the time. It depends on how much current is applied or how much H and B are there. Then C, so again, in part C, we need to calculate here if the air gap is 0, which means the I shape is already attracted now to the C shape. Find the current in the coil for the same flux density of 0.8. So which means, guys, after this arm being attracted, so we have 0 air gap. In this case, how much current will be required in order to have the same amount of flux, 0.8 Tesla? Actually, we don't need to make any more calculations because we already did that in our calculations right here. So since we already calculated two parts, the first part of the MMF is the part due to the magnetic core itself, and the second part is due to the air gap. And now we don't have air gap, which means this part will be 0 now. So this means, guys, the current can be calculated using only the MMF of the second part. So this is the remainder of part B. And part C start from here. So we have now the total F is going to be just the core F or force. So F equals HC times LC now, which is calculated before 184. And now we can say the current equals 184 divided 500, which is 0.368 ampere. If you compare now, you will find that the current will be very small once the relay is attracted or the relay is turned on. So in industry, guys, we refer to the relay positions as open or closed. So this is called normally open relay. Once you energize this relay, so this relay will be closed. So we say this is normally open relay. Okay. So this means, guys, if the relay is open, no energization, so the required current at the start would be 4.19 ampere. And the current will be just 0.3 ampere if the I shape is attracted to the 4.9 to the C shape. So does it mean, guys, the current during the stroke of the relay will be the same current for 4 ampere, 4 point something? Actually, no. So if we did write or draw a relation between the current and the X, and consider X here, X in this portion, X equals 0, and this is the direction of X. So in this case, guys, the current will reduce actually the relation is not linear. I don't know exactly how the relation is. It depends on the magnetic calculations and analysis of this core and how much current needed at every distance, but it can be calculated. So for instance, you can make now like calculation at every distance. So we consider at 1.5 distance and 0 distance, but you can consider at like 1.3 millimeter, 1 millimeter, until reaching to 0 millimeter. So this is the concept. So we can make now, this is 0 to, let's say, 1.5 millimeters. So if the value of x, or sorry, x starts from here, if this is 0, so the current would reduce like that. Okay, so here, this was the start, for instance. Here, this is the 3.19, and the end is 0.368. So this is 3.19 ampere, and this is the end, 0.4 ampere. So this is the shape, guys, of the current. The current will reduce with x value reducing to 0. So instead of saying x equals 0 here, guys, let's say x equal 1.5. And here x equals 0. Sorry for that. So I'm going to say the opposite relation. So this makes more sense. So the current shape is going to be like that. So at high value of x, you have high value of current. At low value of x, you have low value of current, okay? And x equals 0 means you don't have any air gap, okay? So this is the situation now of our relay. So first class activity is required is, for this example, I'd like to see the current value at every distance and draw this curve. So this is the first quick assignment you need to do. So calculate. I'm going to write this after this example. So what we need is draw the electrical current curve versus distance x as x equals 0 at 0 air gap, x equals 1.5 at the distance of 1.5 millimeter with 0.8 Tesla. Okay, so this is the quick assignment you need to consider. Okay, guys, so please solve this assignment and turn it on by this Friday. Okay. Okay. Now, let's move to the next example here. So in this example, consider the magnetic system of example 1.1, so the previous example. If the coil current is 4 ampere, when each air gap length is 1 millimeter, find the flux density in the air gap. So since the air gap distance is going to change, guys, so we expect that the flux will change as well. So the question is, calculate the amount of flux density. What is the value of B at 1 millimeter distance and current is 4 ampere? So this is the opposite of our calculation. However, if you try to solve this just numerically without graphics, it's not going to be very easy. So let's see, guys, what problems we have here. So firstly, this is our relation. Ni equals Hg Lg plus H core L core, which is Bg divided mu naught Lg. So Hg can be replaced by Bg divided mu naught times Lg plus H core L core. Actually, we need to make a relation from this relation here, a relation of a straight line, and use the BH curve and draw this straight line with the BH curve in order to get the point of intersection. So this example will not be easy to be calculated numerically. You have to use graphical solution. So in order to do that, guys, what do we need to do is create a straight line equation from our Ampere's law and draw this straight line on top of the BH curve of our core in order to get the point of intersection and calculate or get the value of B. Why again? If you have a look to this relation here, guys, we don't know the value of H core. We don't know the value of B. We don't know these values. So how can you get the value of B? Okay, so two or many unknowns are exist in our equation. So in order to do that, guys, we have to draw a straight line equation and use the graphical solution. So the solution is, if this is a curve or the relation of B, we need to have B in the left-hand side and move all other terms to the right-hand side. So you have Ni in the left-hand side, move all others to the left-hand side and keep B in the right-hand side, or vice versa, whatever. Okay, so now HCLC can go to the other side. Then you can multiply times mu naught and divide over Lg. So in this case, you will find that B in air gap or in core equals minus mu naught times Lc divide Lg times H core plus N times I times mu naught times divide Lg. This is the value that we need. Do you know the current? We know the current. Current is 4 amperes. Mu naught is constant. Lg is known, which is 1 millimeter each, so we have 2 millimeters. Mu naught is given, so L are there, but we don't have the value of H. So we cannot solve this relation or calculate B numerically. What we can do is, this now represents a straight line equation. The HC is the x-axis variable, which means now this is our slope. and this is going to be the intersection with the horizontal x. So from this relation here, we can say the slope of this straight line is minus mu naught LC divide LG, and we can calculate this slope. And the point of intersection with the vertical x with B, so we can get it Ni mu naught divide LG. So we have all of these parameters, so we can get these values. So we got now 2 points. The point here, and also you can, since you have the slope of the line, you can substitute at in the curve and get the value of h at b equals 0. So if we go back to the relation here again, so substitute at b equals 0 and get the value of h. If you do that, you will get the value of h, which is Ni divide LC, and this is the number. So this is the other point of intersection. Now you can draw this line, and you have the original curve of the cast steel, the BH curve of the cast steel. In this case, the point of intersection here will represent our operating point. This would be the value of H at 1 ampere, 1 millimeter, sorry, 4 ampere, 1 millimeter. And this will be the corresponding value of B that we need. So this is the way, guys, that we can use to calculate the problem in the opposite direction. And again, you have to use the graphical solution in order to do that. Okay, so this was another idea of the example here. And again, you have to use graphical solution. And for sure, in these problems, guys, the BH curve will be given in the exam.